Let's look at pressure now. Pressure is defined as a normal force exerted by a fluid per unit area. Since pressure is defined as force per unit area, it has the unit of newtons per square meter, which is called a Pascal. That is, 1 Pascal equates to 1 newtons per meter square. The pressure unit Pascal is too small for most pressures encountered in practice, and therefore its multiples like kilopascal, which is 1 kilopascal is equal to 1000 pascals, and megapascals, which is 1 megapascal equals 1 million pascals, are commonly used. The actual pressure at a given position is called the absolute pressure, and it is measured relative to absolute vacuum, which is the absolute zero pressure. Most pressure measuring devices are calibrated to read zero in the atmosphere, and so they indicate the difference between the absolute pressure and the local atmospheric pressure. This difference is called the gauge pressure, or P gauge. So P gauge can be positive or negative, but pressures below atmospheric pressure are sometimes called vacuum pressures and are measured by vacuum gauges that indicate the difference between the atmospheric pressure and the absolute pressure. So P gauge is equal to P absolute minus P atmospheric, and also P vacuum is equal to P atmospheric minus P absolute. So let's put this into practice. Like other pressure gauges, the gauge used to measure the air pressure in an automobile tire reads the gauge pressures. Therefore, the common reading of 32 psi indicates a pressure of 32 psi above the atmospheric pressure. So at a location where the atmospheric pressure is 14.3 psi, for example, the absolute pressure in the tire is 32 plus 14.3 equals 46.3 psi. With the knowledge that you have gained thus far, pause the slide and practice this problem. And then once you're done, look at the answer. Let's look at variation of pressure with depth. In a room filled with a gas, the variation of pressure with height is considered negligible, and you will use this assumption when you are doing calculations in thermodynamics. And also, pressure in a liquid at rest increases linearly with distance from the free surface. And in a static fluid system, a pressure increases with depth according to the following equation, which is the pressure at the bottom is equal to the pressure at the top plus the depth rho g, and rho is basically the density of the liquid. Using the knowledge that you have gained thus far, try this practice problem. Express the following using PA, which is the pressure of air, H would be the height of any given column, and rho would be the density of a given fluid. Under hydrostatic conditions, the pressure is the same at all points on a horizontal plane in a given fluid, regardless of geometry, provided that the points are interconnected by the same fluid. And as you can see, the pressure at point A is equal to the pressure at point B, C, D, E, F, and G, which is going to be equal to the atmospheric pressure plus rho GH. But you will also notice that the pressure at point H is not equal to the pressure at point I, the reason being the fluids are not interconnected. A consequence of the pressure in a fluid remaining constant in the horizontal direction is that the pressure applied to a confined fluid increases the pressure throughout by the same amount. This is called Pascal's law. Atmospheric pressure is measured by a device called a barometer. Thus, the atmospheric pressure is often referred to as the barometric pressure. The pressure at point B is equal to the atmospheric pressure, and the pressure at point C can be taken to be zero since there is only mercury vapor above the point C, and the pressure is very low relative to atmospheric pressure and can be neglected to an excellent approximation. Writing a force balance in the vertical direction gives the atmospheric pressure P atm equals rho GH. We notice that an elevation change in a fluid at rest corresponds to pressure change divided by rho g, which suggests that a fluid column can be used to measure pressure differences. A device based on this principle is called a manometer and is commonly used to measure small and moderate pressure differences. So using the knowledge that we gained thus far, let's try to compare the pressures in this system that is given in this figure, and compare the pressures between point A and point B, point E and point F, point B and point E, and point C and point D. So now let's try to answer this problem, and what you'll have to remember when you are solving these types of problems is that in a static fluid system, pressure in the same level is going to be the same in a same continuous liquid. So let's see the answers. So between points A and point B, the pressure in point A is going to be the same as the pressure at point B because they are at the same level on the same continuous fluid, which is marked by red here. The pressure between point E and F are not going to be the same because although they are at the same level, it is not the same fluid. Point E has the fluid that is red in color and point F has the fluid which is blue in color. Between point B and E, of course again, point B and E, although they are at the same level and they are the same fluid, are they continuous? No, they are not. So as a result, the pressure is not going to be the same. And between point C and D, also the same rule applies. Although they are at the same level, are they continuous? No. Between point C and D, there is a different fluid at the top. So the pressures are not going to be the same. So as you can see in this situation that is given in figure 157, in stacked up fluid layers at rest, the pressure change across each fluid layer of density rho and height h is given by rho gh, and the pressure at point 1 is going to be the atmospheric pressure P sub atm plus the pressure exerted by each of the fluids that have a height of h1 for fluid 1 and rho 1, and height of h2 and rho 2 for fluid 2, and height of h3 and rho 3 for fluid 3. So the pressure at point 1, that is P1, is going to be the atmospheric pressure plus rho 1 G1 H1 and rho 2 G H2 plus rho 3 G H3. Let's see how to measure the pressure drop across a flow section. So in this case, a relation for the pressure difference P1 minus P2 can be obtained by starting at a point 1 with the pressure P1 and moving along the tube by adding while you are traveling downward from a reference point, or subtracting when you are traveling upward from any reference point the rho GH terms until we reach point 2. And then setting the result equal to the pressure at point 2, which is P2. Note that when you are traveling from point 1 to point A, we are traveling downward, so we are adding the pressure. And when we are traveling from point B to 2, we are traveling upward, so we are subtracting the pressures. And also note that when we jumped from point A horizontally to point B, we ignored that part because the pressure at both points would be the same.